to welcome Michael Rothgang from Bonn, who will tell us about tooling and automation for scaling Mathlib. Michael?
Thanks for the introduction and for inviting me. And of course, thanks for organizing this meeting in the first place. It's my pleasure today to tell you about tooling for scaling Mathlib. So what are we talking about? Let me show you two graphs to indicate the elephant in the room. So on the left, we see a graph showing the number of files in Mathlib. First for the Lean 3 version in blue, and then the Lean 4 version in red. And you see a roughly linear growth over time. The graph on the right shows the total lines of code, which indicates this is really a linear growth of the library. But it also shows you something different, because it tells you the last year when a line of code was modified. So you see that even though new code is being added, code is also being refactored, extended, improved. So it's really about a continuous maintenance of that library. And that has challenges. It has challenges for users. It means there's continuous churn. You need to update your code to compile with the newest version of Lean. But if you also then upgrade the Mathlib version, there will be lemmas that are renamed, or perhaps files that are split or moved, so your imports change, and you need to adjust for that. Or you could have a lemma that is, say, improved, so it's generalized, but then you need to adapt your proof using that lemma. So for users, you need to keep up with Mathlib. But there's also challenges for maintainers that we'll get back to later. I mean, of course, everything about churn still applies. If I change a definition in Mathlib, all files that use that definition might need adaptations. If you have a large library, you need to think about technical debt. I mean, you perhaps want to have some so you can keep moving, but you need to keep it in check so it doesn't accumulate and slow you down, makes you come to a halt. You will get all systemic issues you can think of, and you want to have tooling to catch those automatically. And the last part is the most important. It's about code review. Mathlib has mandatory code review, which I'll talk about later. So in practice, that means you now have every single PR that you want to review and make sure it is good code. So at the moment, there's about 1,200 open pull requests. So I am a believer that at some point, computers are there to help us and tooling is there to help us. So let's talk about tooling for all of this. What can Mathlib tooling do for you? And I'll examine this question from several perspectives. If you're a user of Mathlib, be it for teaching or some project depending on Mathlib, if you're contributing to it, if you're a reviewer of Mathlib, or if you're a maintainer and you want to make sure the whole library stays together and doesn't explode or collapse under its own complexity. So before I begin, let me emphasize that this is the work of many people, three of which I'd like to mention explicitly, but there's many more whom I can't mention here. So Mathlib for me is really a team project, and all tooling improvements also. So let us get started with tools for users. What can Mathlib tooling do for you if you just want to use Mathlib? Well, the first and perhaps the biggest challenge is dealing with change in Mathlib. If there's a lemma that's deleted or renamed, for instance, that might be the most common case, but it's also the easiest to deal with. Mathlib now has a system of deprecation warnings that whenever a lemma is changed or renamed for the periods of the next 6 or 9 months, or perhaps even longer, you will get a warning if you use the old lemma that tells you the lemma was deprecated, might even tell you why, so you learn something about it, and it tells you which new lemma to use. So your old code will usually still compile, but you'll get a warning and can gradually move to the new way of doing things. The second big source of breakages when files are perhaps moved. So your old import mathlib dot whatever statement does not work anymore because that file doesn't exist, and you need to tweak that import statement. Perhaps the file is split into several, and of course you'll need to change to imports also, or perhaps the declaration got moved. This case is a bit rare, but it's also fairly easy to do by hand. You replace the import that doesn't compile by a simple import mathlib statement, then use the hash min imports command at the end of the file to reduce the imports down to what you actually need. So both of these we also have tooling for, but both of them can be automated. There's in fact a prototype for both of them. There's one for updating deprecation, there's also one for bumping imports. So if you're using Mathlib in a downstream project and you would like to actually use it, speak up. I think the biggest reason these are just prototypes is because nobody said loudly enough, I want this, to actually polish it. There's also different types of tooling if you have a big project that only needs parts of Mathlib and you want to download the cache, perhaps you don't need all of it. So soon there will be a command that allows you to get just the cache you need. If you're on a tight network connection, on a slow network connection, it might be quite nice. There's a second big challenge, which is actually using Mathlib. Because Mathlib is so large, there's no point you can remember all names of all lemmas. So Mathlib has a very strict naming convention that should basically allow you, given the statement of a lemma, to guess what it's named. And that goes very well. But there's some limits. Perhaps you don't know which way that statement is phrased, or perhaps your lemma is one of the unlucky ones that are still misnamed. So there are tactics to actually help you find a lemma in your specific situation. So exact question mark will tell you lemma if it finds one that just solves your goal. Apply question mark something where you can apply it. There's also the right question mark. Yeah. Personally, I like exact question mark more than exact bang, but that's a matter of taste. Yeah, if you don't want to use lemma finding tactics, there's also tools for searching for themes. For instance, Lugal, that we learned about on Tuesday, gives you structured theme search. So it allows you to find, say, all themes mentioning the same function and pi, or all themes that have Jacobi in the name, which there are none of, I think, because Mathlib prefers more syntactic names, or all themes mentioning a ring homomorphism. So I think that's really, if you're new to Mathlib, that is perhaps one of the underrated tools that are more useful than you think they are. And that's worth learning about. At the same time, there are also tools using lateral language search. So if you have the rank nullity theorem, perhaps you just want to search for that. And sure, you could grab through the Mathlib source code, that works well, but you can also do that in your browser. Google and Lean Search do these kinds of things. Yeah, and perhaps an honorable mention goes to the generated documentation, which has the advantage that it's rendered in the browser. You don't need any Lean editor, and it's actually clickable. If you have a type that occurs there, you can click it. Might be prettier than perhaps just reading Lean source code. That's a subjective goal. But most importantly, if you just want to know about all themes in that file, you could just read the documentation in that browser and get some idea what does Mathlib know about this kind of concept. So this is if you're using Mathlib as a dependency. Now, what if you want to contribute? Let me perhaps begin with some more overlooked aspects that we might all take for granted, which is why I'll mention them. So the first one is that Mathlib is developed in the open as an open source project, with most discussions being actually open to anyone on the internet, on GitHub and Zulip. And secondly, Zulip actually has this really nice feature that it allows almost live collaboration. When I was doing conventional mathematics research, one thing that really made it harder to stay motivated is that fact that you will meet perhaps your own work group over lunch, but if other people work on similar things, you only meet them if you explicitly make an effort or at a conference. Whereas on Zulip, you see in much more of a real time when people actually do something. So for me, that is extremely motivating and also really helpful in that it helps share knowledge. If somebody else is working on something, you can know, and you can perhaps find out before you keep doing the same thing and being unaware. I think the Lean and Mathlib community is doing pretty well at being welcoming for new people, which I think is great, and it's extremely important. And then it also wants to be friendly for newcomers. So for instance, by having great documentation, by having focus on good tooling, as opposed to this tooling is horrible, it's never documented, and to have to suffer through it, and if not, then you will just not become a contributor. That's one way to do it, but I really like that the Lean community does different. Then the third important aspect that we already touched on is the fact that Mathlib has mandatory code review. Every contribution needs to be approved before it gets merged. You can't look at it from a point of this is gatekeeping and exclusionary, and it certainly has the potential to be that. But I would like to take a different view at this. I'd like to frame it differently. I see it as a way of teaching and actually onboarding people. You don't need to be afraid that you're doing something wrong and that your code is horrible, because somebody else will look over it and tell you if there's anything that needs to be changed, but also confirm that everything is fine. And it's also a great way to become a better Lean programmer. So I certainly learned a lot when I was just contributing PRs and then getting them reviewed and realized, okay, this could be shorter. There's a new trick that I don't know. Here's a better way to design things. And yeah, you only learn this by experience, but we already learned it, so we can teach you now. So for me, code review is also a teaching tool, a way of onboarding new people. Then the final technical aspect is continuous integration. Whenever you merge a pull request, there's some automatic checks that run and make sure that the code builds and it passes your set of tests. And yeah, that's combined with a not rocket science rule that says you only merge code that passes all tests. Full stop. So these are some perhaps overlooked aspects, some aspects you might know more, some tooling for contributors. So if you have a pull request that renames lemmas, there is a script that generates the deprecation warnings for you. You don't need to write them by hand. The computer can do it for you. And secondly, I've already touched on this, but there's a lot of linters in Mathlib. The idea is that basically, if you have some check that is necessary, it's nicer to automate it, because then the computer will spend the work and a human need not do it. So you can automate some coding style checks, which a reviewer need not tell you. You can have consistency checks, such about the set of simple lemmas, as we mentioned on Tuesday. So you can kind of ways to make sure the code is robust, for instance, by linting against non-terminal sims, as a flexible tactic linter does. Or you even have linters to check for systemic correctness problems. As far as I know, a lot of linters in Mathlib 3 were about problems that you realize this is bad if you do it on a library scale. And then it became checks in Lean 4, so that became even built in. There's no need for a separate linter now. And this is one avenue when there has been a lot of improvements to Mathlib linters in the last year. Sometimes we're evaluating linters from just a Python script that's text-based to a Lean script that's text-based, and now that's a Lean syntax linter due to Damiano Testa and myself, for instance, which means you have more robust linters. They're also a bit faster, and you as a user get feedback much more immediately. There's a cache, so you don't need to rebuild all of Mathlib all the time on your computer. You can have other computers do it for you. Yeah, that's the shake tool, which you use to cache superfluous imports, which is useful on the library level to make sure somehow your build times stay in check. I'd also like to mention a prototype framework for library level refactorings, which I think is extremely exciting. So if you want to replace all occurrences of this deprecated tactic by that tactic, you write a short program to tell lean what to do, and then that program will fix all of Mathlib for you. And perhaps as a final shout out goes to tactics to improve automation. So we've already heard about ASOP, Omega, BV decide and grind on Tuesday. I'd also like to mention the fun prop tactic, which can be, say, used to show this function is continuous because it's a composition of continuous functions. So there are also some technical challenges if you want to scale Mathlib. All of this could be a separate slide and a separate talk, so I'll keep it a bit short. But I would like to mention there is, first of all, a challenge on the core system. I believe that switching from Lean 3 to Lean 4 has sped up math with build times by a factor of 2 or 3. So this was really long planned and perhaps not overdue, but long welcomed improvements to the core system that powers Mathlib and that enables it to scale further. Yeah, core changes drastically and improves a lot, which is extremely great, but it means you need to keep up with it. Mathlib has more than 1 million lines of code, so that's quite some effort, and I'm really glad the Lean FAO has a team of competent people doing exactly that, and also having extensive automation that I'm not talking about. There's been a lot of work spent on speeding up Mathlib compilation. I can start with just looking at some slow files in a profiler and seeing if there's anything that stands out. There's continuous performance tracking, so you can catch regressions that are unintentional. For instance, I in the past introduced the big regression ones by importing lake in a Mathlib file and then realized, okay, perhaps that's not a good idea. Do we actually need that import? And realized no. So there wasn't quite an easy way to speed Mathlib back up. And without performance tracking, you wouldn't have even realized that existed. Yeah, there were big efforts to say we factored the fun-like hierarchy, which then sped up Mathlib by about 20% in terms of instructions. And right now, I think one of the biggest challenges is tweaking the type class synthesis, making that faster, because that's one of the major contributors to Mathlib compilation time. Yeah, there's an entire different topic about technical debt. There's tooling for tracking technical debt, for tracking changes to technical debt. And there's a joint effort to slowly pay it down. And as a final item, I would like to mention that handling imports is more important than you think if you want Mathlib to build in parallel, if you want to reduce unnecessary compilation, and if you want to make it easier to minimize, say, the bug that you found in Mathlib. So let's dive one level deeper into further tooling and challenges for reviewing code. So first of all, if you have a pull request, you need to find a good reviewer for it. Who is able to review that pull request? So there is some automatic labeling for that labels a pull request based on which files it touches. So you have a guess which mathematical areas it corresponds to. Then you can find a reviewer who is competent in that area of mathematics. And secondly, there's now for several months now a sticky summary comment, which we have a picture of in the slide. So if you make a pull request, the workflow will create a comment that tells you if any imports change in any file. So if you have a pull request that wants to minimize imports for a given file, you can easily check how that worked. The script also shows you if you rename the declaration. So you can check if, say, just some code was moved, or were there actually renamings, or if the renamings were the ones you wanted to. And it also shows changes to technical debt metrics. There's a couple of them that are tracked explicitly, and you can see direct changes to these metrics. Yeah, and all of that is obviously very helpful if you want to work on technical debt, if you can directly see what does it do? And this comment is updated automatically whenever you push new comments, so you really have the current state of things all the time. I think these are small things, but easily overlooked how impactful they are. Another small thing is a small bot that signals on Solid if there's a message mentioning a pull request, if the pull request has already been merged. Now, if you see that pull request and it says it's ready for review and you see it's been merged, you can realize, okay, I don't need to review it, it already has been done. It saves you some easy click, but if you save 10 seconds, 10 times a day, every day, it adds up. Let me mention one more social aspect of code review, which is the scaling aspect. Every pull request needs to be reviewed, but everyone can review. If you're new to Mathlib, you will not be an expert on everything, and that is okay. There's usually some aspect which you can comment on. Perhaps you can check if the documentation is understandable, or you can say, is there something in terms of coding style that you would have done differently? Or you can just comment if the pull request matches what you would have thought, and perhaps if there's a design decision to be explained. So even if you're not an expert, there's some things you can comment on, and as you become more advanced lean user, you will know more things to say and slowly learn. There's even an explicit set of guidelines, or so to say, which questions are useful questions to ask yourself for reviewing. So it's not magic, you can do it too. And it helps. Yeah, so there's a group of maintainers who have the final merge rights and pull requests. There's currently 28 of them in all kinds of different areas of mathematics, because it's usually helpful if you look at the formalization of a particular corner of Mathlib, if you know that mathematics very well. And it's also extremely nice if you have several maintainers in one area, because then you can discuss or come to consensus, or one maintainer can be on holiday and that is fine for everyone else. Yeah, but there's not just maintainers. The point is that the reviewing load should be shared among more shoulders. So for this reason, there's a group of so-called reviewers, people who have more experience reviewing pull requests and have done useful reviews in the past. And if they approve a PR, there's a direct mechanism that notifies the maintainers so they can take a look and usually merge pull requests more quickly. And I've done some bit of data analysis, so this actually helps share the load. So every third pull request gets approved by reviewer before it actually gets approved by maintainer. And that is even an undercount, because that only counts those PRs that are approved by a reviewer, but not those where reviewer reviews is basically about to say that looks good, and then a maintainer already comes along and says looks good. Yeah, so I think one of the most important social takeaways is make it a team effort and share the load. And perhaps also make it enjoyable. The relatively recent custom of Johan is to have regular meetings where you do triage and review of pull requests together. In my experience, that's a lot more fun. So, are you ready for one last level of going deeper? There's some more tooling coming up. So, as you see, there's lots of pull requests. And basically, you have a challenge to keep track of all of them. If there's 1,200 of them, I can't easily track all of them in my head. And it's extremely easy for some of them to get lost and to not get a timely response at all. So there is a need for custom editorial tooling. So what do we need from that tooling? Well, it would be nice to keep track of all pull requests that are ready for review and allow for filtering, say, by subject area. Then secondly, it's incredibly easy for a pull request to fall through the cracks. So for instance, there have been cases when there's an intermittent network failure and then continuous integration fails. And the review queue excludes those pull requests by default, because usually that means the PR author needs to do something, but in practice that means it never gets looked at. This is easy to find if you know that you need to search for that, but perhaps you want to have a tool to remind you of these. Yeah, basically, this tooling can help you do the task that a normal triage group would do. Look at certain problems or certain ways a pull request can get falling through the cracks, and then specifically build a tool to point attention towards these. Yeah, you might ask, can't we use GitHub for that? GitHub has lots of great tools. Yes, it does. But at some point you run into limitations. And one limitation might be that you want to know when was this pull request last really updated. And there was a merge conflict that was quickly fixed, perhaps does not count as an update. Or somebody corrected a typo in the description of the pull request, also doesn't really count as substantial change. But for GitHub, it does. So sometimes the incentives to not make any changes to your pull request, so the last updated information does not get renewed. I think we should do tooling that avoids such perverse incentives. And it is possible to do better, but you need a new tool for that. Similarly, you might want to have tooling to give you the total time a pull request was in review, which GitHub also doesn't expose. And finally, when you're doing triage, if you're reviewing the different groups of people who want different information. If you're a maintainer, perhaps you want to look at all pull requests that were already approved by a reviewer and just need you to say, yes, looks good. If you're a reviewer, you want to find pull requests you can review about perhaps in your area of mathematics. Perhaps you're doing triage and want to see, are there any pull requests falling through the cracks? So there's really different kinds of information for different people, and it's useful to expose that separately. So we've built a tool. More precisely, Johan Commelin decided this tool is needed, let's build one, and build a prototype and post it about it. And I had thought about triage on a manual level and got excited because that was one way to automate things, and started for helping implement things. So 3,000 lines of Python code later, we have the screenshots here, as you can see. So at the top, you see the initial landing page that allows you to select what you're actually interested in. Do you want to review a pull request? Are you a maintainer who just wants to look at merge pull requests, at those waiting for you to merge? Do you want to do triage and look at pull requests that are falling through the cracks, whatever that means? And there's also one page if you're a PR author and you want to look at all your PRs and see, are there any that are not in the review queue right now? And can I see why? Yeah, so there's this landing page, and then there's different, well, most of these pages have tables like I've shown to below. So you can see the different columns. There's the number of each pull request. You have the author, the PR title, how it's labeled, but then you also know the total diff, so the number of lines added and removed. You can see when was the pull request last updated, but also when was the last real change to its status happening. So when did this pull request move from waiting on the author to address some comments to being ready for review again? When did it last get a merge conflict? If there was depending on another PR and that PR landed, that's also a kind of status change that counts. Yeah, and I'd like to highlight that all of these columns are sortable, and the sorting is actually intelligent. So numbers are sorted as numbers, titles are sorted alphabetically, diff size is sorted by the total number of additions and deletions, and the last column, total time in review, is sorted by time and days. So it understands the difference between days. You can also have months or hours or seconds, and there's really some semantic understanding of it. And perhaps the second aspect I'd like to highlight, if you look at the total times in review, you see that sometimes it's 3 months, 2 months, a few weeks. And for me, this really highlights you make what you measure. If you don't track these kind of metrics, you will never know. So you need the tooling to be aware that there might be some pull requests that are not getting looked at. How am I doing with time? Do I still have 5 more minutes?
I think you're at negative a few seconds, maybe about 0 right now. So,
Okay,
um,
so I have a slide with technical details. I'll skip that. Feel free to ask me about that. Yeah, let me point out there's an unexpected application. The tooling or the infrastructure used for that is now used in the linting Combi project to track which files in Mathlib have an open pull request against them, which I'm really excited about. And let me end perhaps with one quote. Ask not what Mathlib tooling can do for you, ask what you can do for Mathlib tooling. There's lots of work remaining to be done. You can make a difference. Thank you.
thank you very much.